Hello everyone, it's Anush and Reason. On this slide, we set the stage by looking at the background of the Bootstrap method. In statistics, one of the biggest challenges is estimating the accuracy of results. For example, when we calculate an average or build a model, we often want to know how reliable is this, how much could it change if we had a different sample. Traditionally, statisticians solve this using complicated formulas or strong assumptions about the data, such as assuming it follows a normal distribution. But in many real-world situations, those assumptions don't hold. This is where the bootstrap method comes in. It was introduced by Bradley Efron in 1979 as a way to use computers and resampling to estimate accuracy without relying too heavily on assumptions. So the background is clear. The bootstrap method was developed to give us a flexible, data-driven tool for making inferences when traditional formulas are too rigid or too complex. At its core, the bootstrap is about resampling with replacement. Here's how it works. First, we start with our original dataset, often called the sample. Second, we repeatedly draw new samples from it, the same size as the original but with replacement. Third, for each new resampled dataset, we calculate the statistics we're interested in, for example, the mean, median, or the regression coefficient. Fourth, by repeating this many times, often thousands of times, we build a distribution of the statistics. This distribution is called the bootstrap distribution, and it allows us to estimate variability, confidence intervals, and even test hypotheses. So the main idea is simple. Instead of relying only on formulas, we let the data speak for itself by resampling it again and again. Why should we use the bootstrap method? There are several important reasons. It is flexible, it can be applied to many statistics, not just the mean or the variance. It does not require strict assumptions about the population distribution. Even if the data is skewed or irregular, the bootstrap can still work. It is computer friendly. Before the computer era, resampling thousands of times was impossible, but now with computer power, Bootstrap is easy to run. It gives intuitive results by building a distribution from the sample data itself. The Bootstrap reflects what could realistically happen if we were to repeat the sampling process. So the reason we use Bootstrap is because it provides a practical and powerful alternative to traditional methods, especially in modern data analysis where assumptions rarely fit perfectly. Now, how the Bootstrap works. Suppose we have a data set of exam scores for 10 students, 65, 70, 72, 68, 90, 85, 60, 78, 82, 74. We want to estimate the mean and its confidence interval. So the first step is to take this dataset as our sample. Step 2 is to randomly select 10 values from it with replacement to form a bootstrap sample. For example, one bootstrap sample might look like 70, 68, 85, 85, 60, 72, 90, 78, 74, 65. Step 3, calculate the mean of this bootstrap sample. Step 4, repeat this process thousands of times, each time calculating the mean. Step 5, collect all these means together. They form the bootstrap distribution of the mean. From this bootstrap distribution, we can see the variability of the sample mean and construct a confidence interval. So this step-by-step process shows how simple yet powerful the bootstrap method really is. Imagine a diagram with three parts. On the left, we see the original data set represented as a box of data points. In the middle, we see multiple arrows leading to many bootstrap samples, each of the same size but with repeated values. On the right, we see the bootstrap distribution of the statistics, which looks like the histogram of values collected from all the resamples. This visualization makes it clear. The bootstrap is not just about one sample, it's about simulating the sampling process over and over again using data we already have. The bootstrap is widely used in statistics and data science. Some common applications include confidence intervals, which are estimating the range where a parameter likely falls, standard errors, measuring the variability of statistics without using formulas, bias estimation, checking if our statistic tends to overestimate or underestimate, model validation, testing how stable regression models or machine learning models are across different resamples. Hypothesis testing, using resampling to simulate the null distribution when theory is too complex. These applications show the versatility of Bootstrap. It is not tied to one specific theory, whether we are analyzing survey data, financial returns, or medical studies. Bootstrap provides a reliable way to measure uncertainty. There's advantages of the Bootstrap. The first advantage is simplicity. It is easy to understand and implement. Second, generality. It works for a wide variety of statistics, even those with no standard formulas. 3. Fewer assumptions. We don't need to assume normality or a large sample size. 4. Adaptability. It can handle complex situations such as medians or regression coefficients. And 5th, visualization. The Bootstrap distribution gives us a direct way to see the variability. These strengths make Bootstrap a preferred method in modern-day data analysis, especially when we cannot fully trust traditional formulas. Limitations of the Bootstrap. The computation cost is one of the main. It requires many resamples, which can be heavy for very large data sets. Small samples. If the data set is extremely small, resampling may not capture the true variability. Dependent data. Bootstrap assumes independent observations, so it may not work well with time series data unless modifications are made. Outliers. If the original data has extreme outliers, those will keep appearing in the resamples and may distort the results. So while Bootstrap is powerful, it is important to understand its boundaries and apply it carefully. The variants of the Bootstrap. Over time, statisticians have developed different versions for special situations. Parametric and Bootstrap. Instead of resampling the data directly, we assume a model, fit it, and then resample it from the fitted distribution. Block Bootstrap. Used for time series data where blocks of consecutive observation are resampled to preserve dependence. Bayesian Bootstrap. A version linked to Bayesian inference where weights are sampled instead of resampling observation. These variants extend the flexibility of Bootstrap, making it useful even in complex dataset where the standard version may not be suitable. So, Bootstrap versus traditional methods. Traditional methods rely on mathematical formulas derived under strong assumptions. For example, assuming normality or large sample sizes, these methods work well in theory but may fail in real-world data. Bootstrap, on the other hand, relies on the data itself. It uses resampling to approximate what those formulas try to predict. The difference is like this. Traditional methods are theory-driven, while Bootstrap is data-driven. Both approaches have value, but Bootstrap gives us an alternative when theory is too complicated or assumptions don't hold. In summary, the Bootstrap method was introduced as a flexible way to estimate variability. It works by resampling with replacement and building a Bootstrap distribution. It can be applied to confidence intervals, standard errors, bias estimation, and more. It has clear advantages like simplicity and fewer assumptions, but also has some limitations such as computational cost. Variants like parametric Bootstrap and block Bootstrap extend its use. Compared to traditional methods, Bootstrap is more data-driven and practical in modern settings. This summary helps us bring together the full picture of the Bootstrap method.